Bueno, pues es para nosotros un placer darle la bienvenida a Sean McCurdy del IMATE, de aquí de CEU. Eh, y pues bienvenidos al seminario de análisis en todas partes al mismo tiempo. Sean nos va a hablar de los 188 años de la simetrización. Espero que les guste la plática. Y ya saben, cualquier pregunta, español o inglés, es bienvenida.
Sí. Muchas gracias. Gracias, Amara y Hugo y Antonio por la invitación. Pero voy a dar la charla en inglés, perdón. So, 188 years of symmetrization. We're starting from the date 1838, when Jakob Steiner introduced symmetrization methods to the study of the isoperimetric problem. And therefore, in many ways, these 188 years since he introduced them are also the story of the isoperimetric problem. So let's start with the isoperimetric problem, and then we'll give lots of history looking into this paper in particular, because this is very old, and it's actually on the other side of a revolution. And it's very easy to miss the revolution viewing it from this side. So we're going to take a lot of time to look at this paper and try to see the revolution that was the difference between classical analysis and modern analysis. And then, with whatever time we have left, we'll try and cover another 100 years or so with lots of fun applications. Okay? I will say, when I prepared this talk, my first draft was like 3 hours long. So we'll see how far we get in this 188 years. But I want to start first with the classical isoperimetric inequality. Right? So what does this say? This says among all, and now we need a class of sets in the plane. So let's just do like connected, bounded C1 sets E in the plane. I need another condition with area, let's say equal to some number A, the area, right? What is the conclusion? The ball with area A, right, has the smallest perimeter, right? So this is the statement. This problem is very, very old. The earliest known results are about 120 BCE. So long history here. But we're going to jump in 1701 with Leonhard Euler, who got very inspired by the brachistochrome problem and the work of Bernoulli and others, started to try to solve this classical isoperimetric problem. And it took him 43 years. He finally published something about this in 1744. And this is a landmark paper in the development of the calculus of variations. So he discovered, for example, Euler-Lagrange equations. He also discovered Lagrange multipliers before Lagrange, right? So this is a huge success for calculus of variations, but also a complete failure to prove the classical isoperimetric inequality. He did not succeed. And for the next 100 or so years, Euler continued to work on this, Lagrange continued to work on this, many foundational people in the calculus of variations continued to work on this problem, and they all failed. And so in 1838, right, we have Steiner, who is a Swiss geometer, and he decided that he would publish 5 proofs. So what is this? Steiner 5 proofs of the classical isoperimetric problem. Again, he's just in the plane. That's all we're doing, right? And Steiner is sometimes referred to as the greatest synthetic geometer since Apollonius. He was the greatest classical geometer in 1,000 years or more. And his most famous proof of this, right, which introduced symmetrization, right, is what we'll look at in detail. But the context of this proof is that Steiner looked at 100 years worth of work from analysis in the calculus of variations, and he said, this is too messy. It's too busy. This statement is a geometric statement, and therefore, where analysis has failed to produce even one proof, Jakob Steiner would prove 5, each with different, beautiful, elegant ideas. And he thought this would be like a triumph of geometry over analysis and the calculus of variations. Let's see how triumphant this triumph really is. Hint, it's going to end in failure. Okay, we're going to talk a lot of shit about Steiner. It's going to be great. Okay, so his most famous proof, right, is the one that introduced symmetrization. This is still an active tool in research. I use this in my research. Tons of other people do as well. So let's look at his original proof, the construction. Oops, let's do. Right, so there's sort of a 0th step here, which had been known for a very, very long time. And this is that, well, if you've got a connected, bounded C1 set, which is really all they could imagine, because again, they're on the other side of the revolution, right, for modern analysis. But if you've got one of these sets, then we can reduce to convex sets. That's sort of the 0 step, right? And the reason for this is actually really simple. If I have some nice set, if I take the convex hull, I add area, and I reduce the perimeter just by like projection. You can see that this line will be shorter than this line, right? So we can reduce to convex sets. Now, Steiner's proof begins with, let's say, P be a convex polygon. Very nice. So he has some nice convex polygon, and he's going to let x be some line. Right? So now, I guess, well, I'm just going to draw the thing. So what he does is he looks at all the vertices, and he drops perpendicular lines. Actually, he drops them all the way through. Right? And now, if I've done this right, I have maybe some triangles at the end, but otherwise some trapezoids in between. And then he just replaces, right? Replace the triangles and trapezoids with symmetric triangles and trapezoids. Right, so he's going to replace this with, oh, I need a much steeper. Oh, I've done this poorly. Imagine that I could draw, right? Right. Basically, rather than letting this trapezoid be this way, you replace it now with the symmetric trapezoid. That's it. That's the entire construction, right? Now let's look at his claims. Right. 1, we preserve the area. And we also have, this is perimeter. Decreasing. Well, if you know the formula for the area of a triangle or a trapezoid, right, this, like, involves the base and the height. But since we don't change any of the lengths of the bases, we don't change any of the heights, immediately area is preserved. No problem. To see that the perimeter is decreasing actually relies upon another fact, and that's that among all triangles with a fixed perimeter, the right triangle has the most area. The dual to this is that among all triangles with a fixed area, the right triangle has the least perimeter. And so he's using this, right, to say that actually the perimeter is going down. And Steiner does prove this statement. So he proves this as well. Claim number 2. He extends this to all K convex. Right? So he just says, look, we can do this with convex sets. No proof is given. 3. He then shows, well, this is like a rigidity statement. He says, if I have some convex figure, and I have a line, let's say, through the center, right? And that figure is not symmetric across that line, then this perimeter is strictly perimeter decreasing. And if he can extend this procedure to any convex K, then this is true. His proof works out, right? It's very nice. And his 4th claim is that since the ball is symmetric with respect to all lines through the center, right, it must be the only perimeter minimizer, right? That's his proof. So let's think about this again for a moment. He's got a good proof of this. This works, no problem. He just states this. There's no proof. If he has 2, then 3 works out. And if he has 2, this isn't quite right either, actually. What he has proved is that if you are not the ball, then you can't be a minimizer. So every convex body, which is not the ball, is definitely not the minimizer. So therefore, the only possible minimizer could be the ball, but he didn't actually prove that the ball was the minimizer. And much has been made about this mistake in step number 4, right? Like, this was pointed out almost immediately by the analysts, and Steiner was very angry because he hated analysis. But lots of people pointed this out. There's lots of references to this in the books. No one talks about this one. That's because this isn't an error. Like, this is wrong. It cannot be fixed, right? He did not prove that the ball is the minimizer. This one can be fixed. So it's a gap, right? But let's look at why Steiner couldn't fill that gap. So we're all analysts. We all love calculus of variations. How would we fix number 2? All right, how would we extend this procedure to some convex set in the plane? Oops. Okay, I'll give you, there's 2 ways to do it. Both of them are very interesting, right? So first fix of 2. We could just directly extend this. Yeah, go ahead. We could just directly extend this to convex sets. What are we really doing? Well, we can kind of look at the body as a whole bunch of slices, and we're like symmetrizing each of the slices. So we could say, okay, for some convex set in a plane, we could look at the area, right, of K. Well, this is just like, and I want it like bounded, so we're not running off to infinity, right? Negative infinity to infinity of, let's say, the length, right, of now K, T, dt, where if we have some set K, right, we pick T, That's a t. And then we look at the intersection with k. And then we just replace, well, this length is how we find the area. And then the idea would be to replace this with some symmetric interval of the same. So we might say that the symmetrization in the direction given by x of k, well, this is just the union over all the t in, let's say if this is like a direction x, like x perp, and this is then like t plus the symmetrization of kt, where the symmetrization, of kt is like negative a to a 2 if the length measure is a, right, and is equal to 0 if our intersection is 0, right? This would be like a direct translation. Okay. Steiner can't do this, though. He's a geometer. He hates analysis. What is this? This is Fubini's theorem, right? Fubini's theorem, of course, didn't come out in full strength until later in the early 1900s, but Euler had a version of Fubini's theorem in the 1700s that certainly works for bounded functions, so it would work for this. So he could have, if he wanted to. But fundamentally, this uses measure theory, right? Steiner doesn't believe in measure theory. He's a geometer. He thinks area is a geometric quantity. He thinks perimeter is a geometric quantity, which is a whole other issue. But right now, we're just dealing with area, right? And this formulation is super important when we go to higher dimensions, because it's true that if we wanted to do this, there's a two-line proof of the classical isoperimetric inequality, right? You want to write the perimeter of k is the integral over some interval I, right? And you have like square root of 1 plus f prime plus squared dt plus integral I 1 plus f prime minus squared dt, right? Where this is like the upper function of our convex set. Pretend it's convex, right? And we have the lower function of our convex set. And then just by Jensen's inequality, right? Because this function, x to square root of 1 plus x squared, this is a convex function. So by Jensen's inequality, we immediately have f plus f minus. Boom. And this is the graph of the symmetrized version. So Jensen's immediately gives it to us. Now, of course, Jensen's wasn't given until 1906, so we would have had to wait, 80 years or so. But like the messy analysis gives a correct two-line proof, whereas Steiner had one giant gap that he couldn't fill and one error. So much for the triumph of geometry, right? And especially in higher dimensions, where admittedly we don't exactly have this situation. It gets a little bit more complicated. But in higher dimensions, we have to do something like this because we can't reduce to convex sets, right? There exist sets in 3 dimensions where when you take the convex hull, you increase the perimeter, right? So that 0th order reduction doesn't hold anymore. So we're forced in higher dimensions to consider this type of thing. And this requires measure theory. The problem is about to get a lot worse for Steiner. What's another way of extending this procedure to any convex set? Come on, we're analysts. What's our first instinct? Someone shakes you awake at 4 in the morning to solve a problem. What are you going to try? Approximation. We're analysts. Come on. Like, it's our favorite thing in the world. Okay, so second, fix. We could say, okay, well, given some convex body, again, please pretend it's convex, right? We could just say, oh, well, we're going to take some inscribed polyhedrons. We're going to sort of approximate out. This is the old strategy from the Greeks, right? This is what Zenodorus was doing, right? This is a very old strategy. And it's true that because you're convex, you'll have the area of your PI increase up to the area of your convex body. And it's also true that your perimeter, which is easy to calculate, it's just lines. You take the length of the lines, right, of your PI, will increase. And it's also true that you'll have the perimeter of the ball, which is the symmetrization, the full symmetrization of K, will be equal to the limit as I goes to infinity of the perimeter of the balls which come from our symmetrizing our polynomials, right? And so you want to say, oh, how easy. We know that this thing is going to be equal to this limit, and each of these perimeters is going to be less than the perimeter of the PI by symmetrization. And we want to say by convexity, well, the perimeter of this convex body is going to be given, right, as the sort of the limit of these. We want to write this. And if you write this, then you can indeed conclude. But there is a very subtle problem embedded in this. While it's true that this works, this is fine, for convex sets, right? Because as analysts, we can write out what that perimeter is, right? No problem. If you define the surface area or the perimeter, even in 2 dimensions, right, as the limit of these inscribed polynomials, and you don't interpret this correctly, you end up with an idea, with a definition of perimeter, which is completely useless for isoperimetric problems. This is a story which would take another hour to go into. But essentially, if we're doing this as some sort of geometric approximation, if we're still thinking about the perimeter as a geometric quantity, right, and we're doing this approximation, that fails completely. The work of Goetz in 1913, and later Besekovich in the 40s, and also Rado in 47, conclusively demonstrate this idea, which was later taken up actually by Lebesgue in his famous thesis, where he laid the foundations of measure theory. The really bad idea in that thesis was this idea of surface area. And it is a complete failure. It took until 1950 for us to prove that it's even well defined, right? For graphs. So for general sets, very bad, very, very bad. And the solution, just like the solution to our area problem, was to consider it not geometrically, but measure theoretically. In exactly the same way that the solution to the problems of Riemann's geometric integrals, which had lots of problems with convergence, was for Lebesgue to define a measure theoretic integral. And just as the problems with the algebraic or set theoretic definition of a function were all solved by Lebesgue's measure theoretic definitions of functions, the problems of perimeter, which arise in these geometric contexts, which admittedly don't happen if it's just a convex set, but trust me, they do happen. All of those problems are solved by the correct measure theoretic definition of perimeter, which unfortunately I'm not going to give because it would take much too long, but that's a topic for another time. The point that I want to make is that Steiner was on the other side of a revolution. Right? After Lebesgue gave us the correct measure theoretic notions of an integral, the correct measure theoretic notions of a function, right? These measure theoretic perspectives were later used by other investigators, starting with Besekovich in the 20s. And for perimeter, the correct version is by Cesari in 36. Right, the correct measure theoretic versions were eventually found. But he could not allow himself to use them because he hated analysis, right? And also because he was before the revolution, which is not his fault. But his hating analysis is. And that's why we mock his proofs. Okay, so that's Steiner's symmetrization. That's Steiner's original proofs, right? This is the definition, more or less, that we use. This definition works in higher dimensions as well, right? You can take any direction, you take the perpendicular, you foliate by lines, you take the length in each line, and you symmetrize. That's how it works. Okay, so now let's move on to some general properties of Steiner symmetrization. I'll try to be quick about this so that we can actually get to some applications and see some more history. Okay, so again, of Steiner symmetrization. So the most important property, in some sense, is that this is perimeter decreasing. In higher dimensions, well, in all dimensions, this was finally proved in 1954 by De Giorgi. So it took a long time, almost another 100 years, or more than 100 years. It's also capacity decreasing. Capacity, I mean Newtonian capacity. If you study gravitation or electrostatics or Sobolev spaces or potential theory, that capacity, right? It's capacity decreasing. Very interesting. Okay, well, what's my other property? Norm, right? So we're also norm, no, not that one. I skipped ahead. Convergence, okay. So for all k in Rn compact, there exists some sequence Vi subset of the unit here, such that these are our directions that we're going to symmetrize in. So if we define ki plus 1, if this is k naught, is equal to s I k. I think the indices work out better if I do it that way. Right, so if we do successive symmetrizations in these directions, then these ki plus 1 will converge to the closed ball, because we're doing compact sets, right? And they converge in the Hausdorff metric. Is there anybody here who's not familiar with the Hausdorff metric on compact subsets? Yeah, okay, so this just says you have a two-sided containment. So if this is our ball, for any epsilon that you give, I go out far enough, and the boundary of my new ki's are sort of trapped in this epsilon neighborhood, right? So that this inner part is completely contained in my k, right? And I don't have any part of k which is extending out beyond this, and that epsilon goes to 0. So it's this two-sided kind of thing. Okay, this is very nice. There's also non-convergence results, right? So there exist k in Rn. In fact, we can take ellipses. So very, very nice sets, right? Such that for any dense Vi in n minus 1, so any dense vectors, right? There exists a convergent rearrangement, meaning I can choose some subsequence, right, of this, which will then converge, in this sense, to the ball, right? And also, exists a non-convergent rearrangement, which kind of is problematic because at some point Steiner, in his proof that I didn't mention, definitely says, oh yeah, you do this in a bunch of directions. Yeah, you gotta get closer to the ball. You can keep going to the ball. He doesn't actually do a limit because he hates analysis. But no, there exist sequences where it doesn't converge. It doesn't converge to the ball. So that's really interesting. This is very recent. Lin Wang 2022 is the most recent paper that I've seen. But this was done earlier by Bouchard and I want to say Fortier this is 2012. Right? So fairly recent stuff. People really care about these convergence, non-convergence, how fast do you converge to the ball. These are huge areas that could take several hours in themselves, but we're going to move on. Okay, so in an effort to get back to the history, back to applications, I want to mention generalizations of Steiner symmetrization. I was trying to come up with a list, and I think I counted 7 generalizations of Steiner symmetrization that I knew of, all of which are sort of their own interesting fields of research, all of which could be their own talk. But the one that we really care about here is Schwartz symmetrization, which was put forward by Schwartz in 1884. And the idea is that rather than foliating with lines, let's like pretend we're in R3, right? So you pick a hyperplane, you foliate with lines, you look at the measure, and then you resymmetrize. Why not pick a direction, foliate with hyperplanes, look at the slice, and just replace the slice with the ball of the same measure, centered, of course. Right? That's what Schwartz symmetrization is. Why do we replace with balls? Because they're the perimeter minimizers, right? That's what we expect. And this one is very useful for a lot of applications. Well, they're all useful, but this is the one that we're going to talk about. Okay, so. What time I have left? How much time do I have left? Oh, perfect. Okay, we can do this. Okay, so applications. Number 1, this is to functions. This research, I think, started around the 1910s, although the first published work that I can find is from the 1930s, and continues to the present day. And the idea is, if we can symmetrize a set, we can symmetrize a ball. That's the entire thing. So we define the symmetric decreasing rearrangement of F, right? S such that the ln of F greater than S is less than or equal to Wn, and what do I have? X. Okay. It's a fancy definition. It takes a while to unwrap. What are we actually doing? Given some function f, we pick a height. We see the intersection, right, with the subgraph, and we just replace it. Pretend that this is symmetric. Right, so that at that height, this slice is a ball, and it has the same mass as the super level set elsewhere. Not too bad. So we sometimes call this the symmetric decreasing rearrangement. Sometimes we call it the Schwartz rearrangement, because all we're doing is we're going to each of the super level sets and we're doing Schwartz symmetrization, replacing it with the ball. That's it. Okay. So this object has a lot of really nice properties. So as a short list, right, this is norm preserving for any Banach norm which only depends on, right, the mass of the superlevel sets. So Lebesgue norms, right, by the layer cake formula. Everyone is familiar with the layer cake formula for Lebesgue spaces? I'm seeing nods. Okay, cool. So all your Lebesgue norms are preserved by this symmetrization. But also, because we're analysts, we love studying things and finding just the right space that an object belongs into. And so if you go into harmonic analysis and you see maximal operators or Calderon-Zigman operators, one of the spaces that they developed is called Laurent spaces. It's just a sort of space that you can think of as arising from interpolation between Lebesgue spaces. So it's a much finer way of telling the norm of something. These are all preserved. The generalization of that, Orlich spaces, these are all preserved. And this whole class of spaces has its own name, right? These are rearrangement invariant spaces. This is an active field of research where the main tool is you have a Banach space and you know you can do, this one. You can do this Schwarz symmetrization, right? A lot of active work in this area, which I don't have time to talk about. Another really nice property that I think is worth mentioning is that there are lots of inequalities for these rearrangements. So this is the Hardy-Littlewood inequality. So if I have some f, g, again positive, because I need to be able to do my symmetrization, right, then f, g, dx you have an inequality like this. And if you think about just like a function with compact support, this is pretty obvious because I could have one function with compact support and its translation, and their product would be 0. But when you symmetrize them, you're pushing all the mass together, so now they overlap, right? That's what's going on. This is first proved in the book by Hardy-Littlewood and Polya called Inequalities, 1934. Excellent book if you get a hold of it. Okay, but of course, inequalities, while beautiful, are not just interesting because we like inequalities. We like using inequalities. This inequality gets used to show that on the space of non-negative functions in LP, this symmetrization procedure is actually a contraction in the LP norm, which is quite nice. Also, you can use this in calculus of variations to show the existence of like coupled harmonic systems. If you care about like springs attached to weights attached to springs attached to weights, you want to show there exists a solution to systems like that, you're going to need this. Okay, I think given the time, I'm going to skip over a few of the other very nice properties that we had. Yes, and I'm going to talk about second application. Okay. Because this is a big one. And this is mathematical physics, and this really starts about 1920 and continues to the present. Right. Okay. Yes, I can do this. Okay. Mathematical physics we now think of as like, oh, general relativity, space-time, pew, 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 right? Mathematical physics actually began 1854. Saint Venant, some French guy, I don't know. And he was thinking about torsional rigidity. So you have like a beam, right? And the beam has some cross-section D, right? And you want to know how much force you can twist it with. And in particular, if you're building a building where something's going to be twisting, you want to know what shape D has the maximal torsional rigidity. So it's the strongest. Well, for reasons that I don't understand, because I am not a physicist or an engineer, right? The torsion, right? This is supremum of F in C1C E of 4 FL1 squared. That's L1 squared. And of course, this is D. And supremum. Infimum. My apologies. Two of D. Right? So whatever this constant is, if you rearrange the inequalities, what this tells you is this is kind of like an L1, L2 Poincare inequality. Right? That's how we should think about this. And Saint Venant conjectured that torsion of D is less than or equal to torsion of the ball. Again, of the same cross-sectional area. And there's a formula for what this should be. I'm not going to worry about it. Let's focus on how you would go about proving something like this. Right? So if we had a function and we were going to do something that would preserve the L1 norm, that would be good, as long as we, what do we want? I want to decrease this, which, oh, do I want the supremum? Did I write it correctly the first time? I apologize. I have it, this is why we have notes. It is the supremum. Aha, excellent. Okay, good. Now it makes sense. If we have a procedure that will preserve the L1 norm, but which will, because we want to go up, decrease the energy, then we win. We have a procedure that takes one competitor and produces a better competitor. And then just like in the isoperimetric problem, we might hope to apply this procedure again and again to get better and better and better and pray that it converges to something. Right? Well, this is the other great property of symmetrization, right? It's so important it has its own name. The Pauli-Szego principle, which was done by Pauli and Szego, ooh, surprise, in 1951. Their proof wasn't actually all that rigorous, and so it was like actually proved by Ziemer in 1988, which is very recent, to me at least. It's the year I was born. Okay, so what does this say? I just can't remember what happens at the infinity case, so I'm going to ignore it for now. Oops, what am I doing? Norms. dx. This is it. The Pauli-Szego principle tells us that this Schwartz symmetrization procedure, right, decreases the energy. Oh, take a moment. How many times have you heard about various physical processes, right, that they follow the path of an energy minimizer? Like all of them. And therefore, we should expect this symmetrization procedure to be very useful for a lot of mathematical physics. Hey, excellent. Okay. The proof of this is more or less, it's actually really nice. It comes from the co-area formula, which, given the time, would you rather see a very simple version of the proof, or would you rather see a long list of how this gets used? The simple version of the proof? Yeah, okay, excellent. Yes. Oh, we'll do it. Okay. All right, so let's let F I'm going to give the simple proof of this, and I'm just going to give intuition for the co-area formula. I'm not going to do the co-area formula. This takes like 2 days classes to do. Ugo can tell you. All right. Okay, so let's pretend that our function is linear, right? We've got derivatives, so locally, yeah, it's more or less linear. Okay. We have some interval here, and we have some range here. We want to look at, let's just let P be 1. Well, we're just linear, so this is like the slope times I, right? But what's the slope? It's the rise divided by the run. But now we have multiplied by the run. So this is the length of the range. And now I'm going to do something wild and crazy. I'm going to rewrite this as the integral over the range of 1. But I'm going to write this 1 very. I'm going to write this as the counting measure over the boundary of my super level sets. And actually, I can rewrite this way. What's going on? Well, as t changes, there's no boundary, so I get 0, 0, 0, 0, boom. I hit boundary. What's the size of the boundary? It's just like one-dimensional, right? So it's 1 point, so I get a 1. And I get a 1 all the way up through the range, and then suddenly there's no more boundary, right? And so the general co-area formula tells you that you can do this change of variables, right, for a much wider class of functions. Again, we need the correct measure theoretic definition of perimeter for this, for the sort of largest class of functions. Again, we are post-1902 measure theoretic revolution. We are modern analysts. Yeah. Okay, so this is the co-area formula. And once you have this, oh, polyazago. It's a snap. Start with this. Let's let P be 1. I don't want to deal with it, right? We have, for P equals 1, we just write it in terms of the perimeter. But then when we symmetrize, perimeter goes down. And then we just use co-area formula to push it back now to the energy of the symmetrization. Ta-da. So this is the principle that is behind so much of these early mathematical analysis results, which I will now write some of. I'm just going to do the early ones, but they are just very beautiful. Okay, so we have 1854. Saint Venant has his conjecture, right, about the torsional rigidity being maximized by the ball. I want 18, this was 70s, right? Yeah, 77. Lord Rayleigh, right, well, he made a lot of conjectures in this paper, but the two that I want to talk about are balls minimize base frequency. So if I have some domain and I let it be like the membrane of a drum, right? If you hit it, it's going to vibrate, makes a pretty sound. you can break up the vibration into different frequencies. The base frequency is the lowest frequency. And Lord Rayleigh conjectured that the shape which has the lowest base frequency is the ball. He also conjectured that balls minimize capacity. Again, if you like potential theory, Sobolev spaces, capacity, very important. Okay, so these are the conjectures. Let's get the results. So Faber, 1923, and Kron, 1920. I think it's 5 and 6, right? Yeah. Right. Prove. Right. They finally prove Raleigh's conjecture on the base frequency. And this is actually an inequality regarding the first eigenvalue for eigenfunctions of the Laplace for this domain. So this is really an inequality for elliptic PDEs. And this is still a huge area, still lots of active research. They still use symmetrization. Right. Okay. For, what do I have? Oh, Zago. Which one is this? So solves Raleigh's conjecture number 2. So Zago then proves that balls in fact minimize capacity. 5. What do we have? Oh yeah. Polya 1948, right? Yeah. Solve the conjecture. Sorry, my handwriting is getting worse. But Polya finally solves St. Venant's conjecture. And then, after all of this, what are we at? 6? We have Polya, Zago prove the Polya-Zago principle. And this is, what, 1951? Right. We finally get the proof of the Polya-Zago principle. So it took a very long time where people were using this property of symmetrization, that it was in fact energy decreasing. This is the key idea. But it took a very long time for them to sort of realize and formalize this. So it's quite a lot of work here. I think. Oh, okay. I don't have a lot of time to talk about application 3, but I will take a minute or two just to mention a few things, and then I promise I will stop. Okay. This is 2006. Okay, so symmetrization is used to prove the isoperimetric inequality. And it's really this property of symmetrization where the perimeter goes down that is being used in the Polya-Zago principle, in Faber-Cron's estimates, in also the Sobolev inequality, right? Which, as analysts, we love the Sobolev inequality. It's so beautiful, right? And in fact, the isoperimetric inequality is equivalent, logically equivalent to the Sobolev inequality, is logically equivalent to Faber-Cron's estimates, is logically equivalent to Polya-Zago, and a few other types of estimates, right? And so there's all of these things that are connected. And the general program that has been extremely popular in the last 20 years has been to take one of these geometric inequalities and first characterize equality, and then 2, prove quantitative stability. If I have a C2 function with a unique minimum, stability tells me, right, that the values of my function can't get close to the minimum without the inputs also getting close to the minimum. Right? You can think of this as like a Taylor expansion. Right? Yeah, plus higher order terms, but forget those, right? So stability just says, like, qualitatively, if your values get close to the minimum, your inputs have to get close to the minimizing input. Quantitative stability involves estimating what this constant is, so that you prove something, make sure I get this, by some constant, x minus x min squared. You're going to prove there exists some constant such that you have an estimate like this, except you're not dealing with the C2 function, you're dealing with the functional of the perimeter, and your domain is all measurable functions, right? Or your functional is the LP energy, and your domain is basically all W1P, right? This program of trying to characterize the equality case and then prove quantitative stability is very hot in the last 20 years. Like Figali got a Fields Medal for his work in this. There's multiple annals papers that are doing this. So this is a really, there's a lot of attention on this area. And I will end, sorry for going a few minutes over.
Does anyone has any question? You can ask in Spanish if you like.
Basically everything has a much bigger story with it. So please.
Thank you for your talk. In this story, do you know in what moment appears the Gaussian isoperimetric inequality?
Yes. So this was proved by Cyrilson and Sudakov and Borel independently in the 70s. I can get the exact dates if you want, but sometime in the 70s. They didn't use symmetrization. They actually used like stereographic projection from like higher dimensional balls, and they used an isoperimetric inequality on the sphere, right? Who introduced symmetrization on the sphere? Polya and Zago in 1951. It was one of the generalizations of Steiner symmetrization, spherical cap symmetrization, and they used a version of this in order to get their original proofs. The nice proof by Earhart in 82, 83, and 84 extends what we think of as the correct analog of Steiner symmetrization and Schwartz symmetrization to the Gaussian space. And I will say that the anisotropic Gaussian space didn't start until like, I think it was 2 years ago. One of my collaborators was the first one to start studying that in this way. Yeah. So yeah, and like the program is the same. He tried to characterize equality, and right now we're writing up a paper which gives the quantitative stability. Right. So this is, yeah. Preguntas.
Anyone?
Maybe the first one is more about physics. On the board, you have the torsion function, the torsion formula. When you know when something will be break when you twist.
This is actually a very subtle problem, because the equations which govern, I'm going to get the names slightly wrong, but if you if you have something and you like bend it a little bit and then it bends back, right? This is like an elastic reaction. Those equations are completely different for if you bend it past the region where it's governed by elasticity, and then you actually have permanent plastic deformation. Those equations are completely different. And so I'm sure that engineers have like formulas for when this happens, right?
Sí,
But I don't
formulas.
actually know.
I know this more about physics.
Yeah,
Physics,
but this is a very important point
Uh-huh.
when you go past the elastic domain, right, and begin to obtain like plastic deformation, right? Yeah, that's a very important point, and there's a transition in the equations that your material will follow at that point. I hope that
Sí,
addresses.
más o menos.
Yeah,
Sí,
más o
sí,
menos.
sí,
Perdóname.
solution. And the next one, you told about the approximate solve when you use polygonals in a convex set. In a convex set. My question is, if I have a convex set, how I can inscribe on polygonals
So
in a
It-
arbitrary
yeah,
polygon.
in arbitrary dimensions.
In an arbitrary convex set. Sorry.
Yeah. So there's, in some ways, if you start with a convex set, then you don't run into the problems that you run in by making a general definition of trying to extend the notion of
The
perimeter or
polygons.
surface area to more general sets. If you start with an arbitrary convex set, why am I drawing a hole? It's convex. Pardon. Right? You can sort of blow it up so there's like a sphere inside,
See?
and you can just project points in here, and now you can take some net of points on your sphere and just use your map, right, to get, well, you can triangulate the sphere or give whatever polygons you want, and then you can just map this onto your convex set.
Okay. Well, see.
So, yeah. And as long as you only consider convex sets, this is no problem. You will get that your limit of polygonal approximations will give you the surface area. But, for example, this idea of taking the limit of polygonal approximations sucks for the following reason. There exist fi from Sn minus 2 into, oops, n minus 1, n minus 1 into Rn, right? Some maps like this, where we're going to use polygonal approximations based upon these maps, right? Such that fi Sn minus 1 converges in the Hausdorff metric, right, to the entire closed ball, but the area, right, the surface area of our fi goes to 0. This is and there's an umlaut, I think it's on the L, in 1913. Even worse, Besekovich, who founded geometric measure theory. This is sometime in the early 1940s. He showed that the same thing. There exists a sequence of fi n minus 1, such that the well, okay. These also go to 0, but the surface area of the fi Sn minus 1, no, the volume, what am I talking about? Volume n, and this is Bn, B1, is always greater than 1/2,
Medio. Okay.
right? So you have non-empty interior. You have volume 1/2 mass inside, but the area, right, the surface area goes to 0. And this tells you that this idea of approximating polygons understood from a geometric perspective, right? Well, what is the surface area? Well, we just take the area of the polygon. We know how to calculate that, right? That geometric intuition is utterly useless for isoperimetric inequalities. There can be no inequality, right, saying that, well, the area has got to be bigger than or equal to something times the volume. That's the isoperimetric inequality. if the area goes to 0 and the volume is positive, right? So this notion, this geometric intuition, is a pre-revolutionary, pre-modern analysis idea of perimeter, right? And there's a lot of other ideas of perimeter. For example, Minkowski in 1903 had a paper where he introduced mixed volumes. This paper founded modern convex analysis. Okay. Very important, where he introduced a different idea of perimeter, which is still used by like probabilists and things like this. It's not a properly measure theoretic notion of perimeter, in my opinion, for very good reason. But the correct measure theoretic definition was really like discovered by Cesari in 1936, and then later expanded upon by DeGiorgi 54, 58. So we have a good notion of what the perimeter should be, but it requires a lot of measure theory. Yeah, it's not a geometric notion. It's a measure theoretic idea. And that's why it's the correct notion. Not just because I love measure theory, right? But because it solves all the problems that the other definitions have, right? Yeah, so.
Okay, great.
I ask one question, please. I talk about application this polarization technique you talk in this theory. Is possible use this technique in, for example, free boundary elliptic problems?
Do you have any particular free boundary elliptic problems? Are you thinking about Alt-Caffarelli style problems?
Caffarelli, Stampacchia, classical reference?
Yeah, so the answer is yes, although the examples that I know about are fairly simple. So let's say you want to model two-dimensional water waves.
Okay.
Who doesn't, right? Okay, so you have some wave profile, and let's make it periodic so we can just follow one period, and so it doesn't change. It's a standing wave. We're just going to follow it, right? So this will satisfy some equations. This will be, you can get these solutions more or less if you're minimizing. Omega here will be some window that we're using, right? And you have squared plus, and then you have, if I want this to be y, x, because again, just two-dimensional waves, I want this to be y characteristic function of u positive d xy. Right, so I just take the function in the first coordinate, right? Notice that this degenerates. So the traditional Alt-Caffarelli regularity theory, out the window if it touches, right? So in date's gone, Stokes' theorem, right? He conjectured that there would be a one-parameter family of waves, right, which would be parameterized by height, and that the tallest wave would touch this line, and you would have a singularity. Right? All the other ones would be smooth. Right? It took a really long time to prove that this happens. Toland was in on it. A couple other people. I can find all the citations if you're interested. But this has not been well. They used other techniques. This has not been well studied by the free boundary community. In particular, we have not proven the existence of this singular point through free boundary methods. There is some work by Arama and Leone and Gravina, where they set up a very simple box, and because they set up symmetric conditions on the boundary, they're able to use symmetrization to say that actually the wave profiles are symmetric. And this helps them get partial results towards this. So there are definitely examples in elliptic free boundary problems where this has been used. this is the only example that I'm deeply familiar with.
Because my ask for this question is, for example, the Laplacian operator not have a maximal principle.
Yeah, okay.
Is
Yeah,
possible?
yeah.
Is possible by this technique, or have one maximal principle?
That I don't know. Yeah. The moment you go into P Laplacian for P not equal to 2, yeah.
Okay.
But
Okay.
I don't know. No, say.
Okay. Thanks. No, because no, in this moment, or not have a maximal principle
Yeah.
for the Laplacian.
Yeah.
Have many questions about this maximal principle. I think it's possible with this technique, or have a maximal principle in bow, in domain, regular domain, in this case.
Yeah. I mean, the principle makes sense. You would need to extend this to your non-local derivatives in some way. I don't know if someone has done this yet. Yeah, but yeah, it would be a very interesting question to see if this applies to like non-local derivatives, right? Or fractional derivatives. Yeah.
We don't want to take it more longer, so if someone has another question to Sean, please just get close to him, and that's it. But please, first, thanks again to Sean.
Thank you so much. Yes. Oh.